Hi, welcome to the last class of Math 408, L functions and sphere packing. Today we're going to talk about calculus of variations. So the reason is this is one of the ingredients that comes into play in the analysis. And the goal for the semester is to get you to the point where you can now read the very technical papers, as well as this is supposed to be a capstone experience where we pull together a lot of the things you've seen from a variety of classes. And so again, if anyone is interested in continuing this in the spring, just let me know. All right. So we were looking at the paper by Cohn and Elkes, new upper bounds on sphere packings 1. If we continue, of course, we will be looking at paper 2. And we ended the last class with a little part that was highlighted. We will show how to use a calculus of variations argument to find functions that prove that bound. So when I was an undergraduate, there was a phenomenal class taught on calculus of variations. It was almost not offered because only 2 of us signed up for it, but it was absolutely wonderful. I was a math physics double geek at the time, and it was a great class that showed the connections between the two, how a lot of physics problems really inspire a lot of the math problems. And this is worth talking about as we end our time together. Where do problems come from? There's no limit to what you can study. And as an editor at many journals, I have received a diverse list of problems that people think are worth studying. One year at Small, I had some of my students looking at one of these submissions, and they came back and said, Professor Miller, yes, there's only 6 references, and all of those papers are by the 2 authors. Yes, and what can you conclude? And so, while you can study anything you want, it's nice to study things other people find interesting as well. So today, a lot of what we're going to do is inspired by physics. You could even call the sphere packing industry inspired by physics. But we're going to see some really nice mathematics develop. And I will try to connect this to math you have seen at the start of your career. All right, so we're going to start off with optimization in 1 dimension. Can someone tell me how would we find the optimal values of a function? And what kind of conditions would you want to assume? So what should we assume about our function?
Do you want continuity?
Yeah.
I think at least continuity.
Maybe differentiability too, if we're doing calculus.
So continuous, differentiable. What else? All right, so we'll do continuous differential. So how do you tell where such a function has a maximum minimum?
Differentiate it.
All right, so take the derivative.
Find critical points.
Take derivative. Find critical points. So these are x such that f prime of x equals 0. And that's what we do.
Looks good.
We also have to look at endpoints.
Endpoints. So when I teach this, I actually run into the wall of a classroom, and I have my speed varying, and I ask, where was I traveling fastest? So this is probably one of the things I'm happy that it's now a remote class, so I'm not doing this. It's not enough to just find the critical points. Now, in 1 dimension, endpoints is not a big deal. At most 2 in 1 dimension. So that is not a huge deal. A lot of this comes down to the algebra. In solving, say, f prime of x equals 0. The calculus is right here. But once we take the derivative, then it all becomes a algebra problem can we solve. So does anybody remember the definition of the derivative?
The limit definition?
Sure.
So you do the limit as h goes to 0 of f of x plus h minus f of x over h.
Yes. Give me just 1 second. All right. There's some issues going on with the schools, and I just need to make sure that that was not related to that. Okay. So it was the limit as h goes to 0 of
f of x minus h, or f of x plus h. Doesn't really matter, I guess.
Yep.
Minus f of x
Divided by, okay.
over h. Yeah.
So this is our standard definition. And then the reason that the critical points work is if, say, f prime of x is greater than 0, then if we look at what's going on here, and if x plus h is a little bit larger than x, for this limit to be greater than 0, eventually, if we're close enough to x, f of x plus h has to be larger than f of x. And similarly, if x plus h was a little bit smaller, in order for this limit to be positive, well, if h is now negative, the numerator has to be negative, so f of x plus h would have to be lower. And so this shows us that we cannot have a maximum at x if f prime of x is greater than 0. So no max or min. Similar result if f prime of x is less than 0. So f prime of x equals 0 is what kind of condition?
Necessary but not sufficient.
It's a necessary but not sufficient condition for a max min. And in a lot of situations, there's not going to be that many points to check. All right, so this is one dimension. What about several dimensions? So we have both the interior points and then we have the boundary points. So how would we find our candidates? So in the interior, what do we do?
Gradient.
Okay, gradient of f. And what should be true about the gradient of f on interior?
Well, at mins and maxes, it should be 0.
Okay, 0, the number is 0, the vector.
I guess the vector.
0, the vector. You know, it's been a while, I think. df, dx1, df, dxn. That's our gradient of f. And what about the boundary? See, unlike one dimension now, there's infinitely many points on the boundary, so it's a little bit non-trivial.
You make the boundary into a line and then evaluate the function along that line.
Okay, so what do you mean by make it into a line? Because the boundary could be several dimensions. You know, here's an example where the boundary is 2 dimensions. You could take some curve, you know, C, maybe from an interval 0, 1 to your surface. And you could look at some new function, g of t is f of c of t. And now this is a one-dimensional problem. And g prime of t, we would use the chain rule. It would be the gradient of f at c of t dotted with c prime of t. So this is kind of like a directional derivative. So this is one way to do it. Another is if we have the boundary, say, you know, the curve or the surface, you know, g of x equals 0, we have Lagrange multipliers. So what we would have here is we would have the gradient of f is some multiple of the gradient of g, and g of x equals 0. So if we have n variables, when we add lambda, we would now have n plus 1 variables. x1, xn, and lambda, but we would have n plus 1 equations. Df dxi equals lambda dg dxi, and g of x equals 0. And the reason this is true is if, let me stop the share for a second, add a slide. That's right. I keep forgetting I can actually pause things with Zoom. So do people see the blank screen now?
Yes.
So if I have, some surface here, and here is the gradient of G, normal to the surface. If I have my gradient of F, if the gradient of F is not entirely in the direction of the gradient of G, then that means I can write it as something in this direction and something in this direction. So I'm going to try to just go like this so I can actually, have the different colors. So here would be the gradient of G coming up like this. And so if my gradient of F is not a multiple of the gradient of G, if it's not in the same direction, then if I flow in a tangent line, my function is going to either be increasing or decreasing. And so it can't be an extremum. Is that clear? So we need the gradient of F and the gradient of G to be parallel. And then more advanced is think about multiple constraints. Say G1 of X equals G K of X equals 0. So maybe you now have multiple things that must be satisfied. Okay. So continuing, the next question is, what does it mean to be differentiable in several variables? Here is differentiability in one dimension. And instead of writing x plus h, I could, if I want, write x goes to a. Doesn't really matter. Is it enough just for the partial derivatives to exist to force the function to be differentiable?
No.
Okay, why not?
Because you can have some weird function which is differentiable in every direction, but not in like in the in-betweens, maybe.
Good. So this is a point that is often glossed over. And so consider the function f of xy equals xy to the 1/3. It's probably not clear that I want the whole thing to be the 1 to the 1/5. So I'll just add it like that right now. So if we try to calculate the partials are all going to be 0. And the reason is we go back to the definition, and if we wanted to calculate, for instance, df dx at 0, 0, it would be the limit as, say, h goes to 0 of f of h comma 0 minus f of 0, 0 over h. But what is f of h 0?
That's just
Zero.
h y to the 1/3.
It's just h times 0 to the 1/3.
Oh yeah.
So it's
So it's always 0.
it's always 0. Because the limit as h goes to 0, h is never equal to 0. We just get 0. So the partial derivatives along the coordinate axes for this function are going to be 0. But if we came along a parabola y equals x squared, then we would have, at that point, the function x cubed to the 1/3, which would just be x, and that's not going to have 0 derivative. So just because the partials are all 0 does not mean the function has 0 derivative. So does anybody remember the correct definition of what it means for a function to be differentiable in several variables? You may not have covered that in math in Calc 3.
Every directional derivative exists.
Okay, now that may not be enough, because for directional derivatives, do you mean just along any straight line? Because you could spiral in. Yeah. I could give you some kind of strange shape like this. I can give you a function that has a limit of 0 along any straight line and along any parabola, but not along a cubic. So this is one of the differences between several variables over one variable. In several variables, it is a huge deal to be differentiable. So does anybody remember what is the definition to be differentiable?
You need it. At all point?
If I were to guess, based on what Sasha was saying, maybe we need to extend that to all possible paths.
So one possibility is to say along all possible paths. That might give you a correct definition of differentiability, but it may be practically useless because now you would have to check every possible path. In one dimension, it's really nice. There's 2 paths to check. It's not a big deal. So it is possible to revisit the definition of derivative. Here is another way of writing the definition of the derivative. So we would say f is differentiable with derivative f prime of a if f of x minus f of a minus f prime of a times x minus a over x minus a equals 0. And here f prime of a is just notation. So can anybody interpret what we've just looked at? So what does f of a plus f prime of a x minus a? What kind of object is this?
First order Taylor.
First order Taylor. And so geometrically, what does it look like?
It's a line.
It's a line. So here's my curve, here's my point, and here's my line. So what we're saying is a function is differentiable at a point if when we look at this limit, it goes to 0. So this is the value of the function. This is like the tangent line approximation. And what we're saying is it's so good that even when we divide by the small number x minus a, it goes to 0. It's not too surprising. If the function is just continuous, then if we didn't divide by x minus a, it's going to be a decent fit. But it's got to be such a good fit that even when you divide by x minus a, so the generalization to several variables is the following. Is, the bold means we're using vectors, and we look at f of x minus the tangent plane approximation. What do you notice that's different from the bottom over the top?
Magnitude.
Yeah, we're taking magnitudes. Why can't I just divide by x minus a like I did before?
Because we have vectors.
We have vectors. You can't divide by a vector, but you can divide by the length of the vector. And so this is extremely similar to what we did before, but this shows you the power of rewriting expressions. So out of curiosity, how many of you have seen this as the definition of the derivative in several variables, that this must be true for the function to be differentiable? Okay, I am now very glad that I changed what I was going to talk about today to spend some time on this, because this is something you should see. You should see, what does it mean for a function to be differentiable? This also, I think, highlights to you how easy it is to think you know something but not. So I want you to tell me how you would calculate the derivative, or what is the derivative? What are the derivatives of f of x equals x squared, f of x equals x to the 3/2, and f of x equals x to the square root of 2. So what are the derivatives?
First one's going to be 2x.
Yep. Second one,
3/2 x to the 1/2,
good. And the third,
and 1/2
2.
x.
Root 2x to root 2 minus 1.
good. How do you calculate the derivative of the first?
Expand out x plus h squared.
So f of x plus h is going to be x plus h squared. We use the binomial theorem. More generally, if we had x plus h to the n, we can do that as well. And all we need to know is it's x to the n plus n, x to the n minus 1h, plus terms with h squared, h cubed, and higher. So this one follows just from the binomial theorem. Can we use the binomial theorem for x to the 3/2?
If you have like the fractional binomial theorem, yeah.
Right, but you need to have the function to be differentiable first before you can use the fractional binomial theorem. This is the same issue we had with L'Hopital's rule for sine of x over x. You first need to know the derivative of sine is cosine. So we can't use the binomial theorem. So there's two ways we can do it. One is we could say, let's let g of x be f of x squared, which is x cubed. Then g prime of x is 2 f of x, f prime of x is 3x squared. So f prime of x is 3x squared over 2 f of x. And when the dust settles, you'll get the same thing. The other thing you could do is you could have x plus h to the 3/2 minus x to the 3/2 over h, right? One of the big things in math is to multiply by 1. Anybody know a good way to multiply by 1 here?
X plus h to the 3/2 plus x to the 3/2.
Beautiful. And so when we do that, then the top is going to be x plus h cubed minus x cubed. Now we can use the binomial theorem. And the limit of the bottom is going to be approximately 2x to the 3/2 times h. So there's two different ways we can handle this. For the third one, we have to use the fact that f of x is x to the root 2 is e to the root 2 log x. And now we use the chain rule. So they all, it's the same rule every time. You know, the rule is the derivative of x to the r is r x to the r minus 1. But the proof is very different depending on whether or not r is an integer, rational, or a general real number. And again, you know, this is, you know, capstone course. This is our last chance together. This is my last chance to try to show some of the things you've seen and just how careful you have to be and how easy it is to accidentally assume something. So when you first prove the rule, you might have only proven the rule in the special case when you have an integer and just assumed you could use it every time. Right. So turning now to the main part of today's lecture, the calculus of variations. So one of the earliest problems, I think it was the second one, was the brachiostochrome curve. So you want to figure out how to have, oops, it says my internet connection is unstable. Okay, if anybody has trouble hearing me, please let me know. So we want to, you know, write down a curve going from one point to another. So you're given the two initial points, such that an object will fall in the shortest amount of time from one to the other. And so, you know, this is going to be a physics part of the talk. We will have a frictionless surface where we don't have to worry about anything like that. So this is a very nice problem. And it was posed by Johann Bernoulli. And I heard there were initially 3 people who solved it. His brother Jacob, which pissed him off, L'Hopital, and an anonymous submission from England. And so you can read the paragraph if you want later, but basically Newton came home one day, he was working at the Royal Mint and worked all night and developed a lot of the calculus of variations, a lot of the ideas, and sent back his solution anonymously. And this is where we get the very famous remark, I recognize the line from his claw mark, just that, you know, he could tell that this anonymous submission must have come from Newton. Right. So the first object we need is what's called the fundamental lemma of the calculus of variations. So we have a function from 0, 1 to r to the n. Our function f is continuous, and it has a really interesting property. Whenever we take the dot product of f with h and integrate from 0 to 1, we always get 0. And here we're assuming h is a C2 function, so twice continuously differentiable, and h of 0 and h of 1 equals 0. And then the claim is that this forces f to always be 0. So any thoughts on how we might prove this? Any idea? So we've got integral from 0 to 1, f of t dotted with h of t dt equals 0, h of 0 equals h of 1 equals 0, h twice continuously differentiable. And you can choose whatever h you want. And the claim is the only function that works is the function that's identically 0. So in some sense, this becomes a way to tell if two functions are the same. We can look at their difference. And if the dot product of their difference with h is satisfying this is 0, then the function must be identically 0. Another way to view this is the more information we have, the more we can conclude. And so if instead of knowing the integral was 0 against all functions h, what if we only had some restrictions? What if h was just continuous? Would that be enough? the wider class of H, the more we hopefully know. So the proof isn't too bad. So let's go by contradiction. Assume there exists an X such that f of X does not equal 0. So we have, let's make sure it's not school. Hello. Okay, can people hear me? Oops, uh-oh. Can people hear me? Hello?
Yep.
Okay, so imagine
Yes.
some point X.
We can hear you.
Yes, okay, good. So we have some point X where the function is not 0. What do we know is true? We might as well assume, without loss of generality, f of X is greater than 0. What do we know is true near X?
It's positive.
It's positive because we have a continuous function. So there's got to be some small window, X plus delta, X minus delta, where in that window, here's f of X, here's f of X minus epsilon. We have to be at least as large as f of X minus epsilon in that window. So what we want to do now is we want to choose a function h, which is 0, and it maybe spikes up like this and comes back down. So we want h of t to equal 0 if x minus t, say, is greater than delta over 2. And then we want h of t to be greater than or equal to 0, and we want maybe a spike. So one thing we could do is we could do a triangle spike. But what's wrong with a triangle spike? So why can't we just...
Not twice differentiable.
Yeah, it's not differentiable. So we need to adjust this. You'd love to use the Gaussian, but the Gaussian is not going to be going all the way down to 0 continuously over here. And we've got to worry about what's going on at these points. So there's different classes of functions you can look at. It's been a while since I've played these games. For simplicity, do you agree that I can just do this on the interval -1 to 1 and then just rescale things? Is that okay? So what if I looked at the function e
Yeah.
to the,
Yeah.
Yeah,
to the
that
1
should be
over,
fine.
so I look at the function e to the 1 over x squared minus 1. And so if I try to look at this, as x gets closer and closer to plus or minus 1, then the denominator becomes an extremely small negative number. So the function is going to 0. So if we take this, for the absolute value of x less than 1, and 0 for the absolute value of x greater than or equal to 1, that should give us a function that'll look like this, and it will be 0 now at -1 and 1. And it will take on its largest value at 0. So it's a fun game, or at least it's a fun game for many of us, to try to construct functions that have all of these different conditions and constraints. And so this would be our function h of x. So we can actually find good test functions like this. The way I often view this is inspired by physics. One of the best quotes I ever heard is, imagine you want to understand how a grandfather clock works. So the way you're going to do this is you take two grandfather clocks, you accelerate them up to 99.99% the speed of light, you then smash them together, and you look at all the stuff that comes out, and you use that to deduce the internal workings of the grandfather clock. To some extent, we're almost doing the same thing here. Instead of having a grandfather clock hit a grandfather clock, in nuclear physics, what you often do is you take a nucleus and you shoot neutrons into the nucleus and you see what happens. Here, instead of shooting the neutron, we're shooting test functions. And we're doing these calculations and we're trying to see what comes out. Okay, so the next part is, now that we have this, the big thing in calculus of variations, the first major result, are the Euler-Lagrange equations. So we're going to look at a space of curves that are at least twice continuously differentiable. So we have some function from 0, 1 to our space, and we know the initial points. It starts at P, it ends at Q. And then we have some function L, and we want to do something to that function L. And that function L is going to depend on the position. It's going to depend on how fast the position is changing, and it's going to depend on the moment in time. And then we look at this integral, and we want to find what is the choice of curve x that will minimize or maximize this. It is not initially clear why one would care to do this. And we'll see shortly that it turns out that there's a lot of problems in mathematical physics that can be posed like this. And so what we want to do is, this is called the action. And what we want to do is we want to see, well, what would happen if we change things a little bit? And I see a comment that it says the audio is super laggy. Are other people having issues with the audio? All right, so I'm seeing other people are having it as well. This might explain the error messages I'm getting that my internet connection.
Yeah, I think it's a little delayed, but I can hear everything fine.
Okay. So this might just be inspired by the warnings I'm getting that my internet connection is unstable. I now feel very glad that I came into my office today and decided not to lecture from home, to take advantage of the better Wi-Fi at Williams. So the idea is, imagine you have your action. It's going to be a function of your path. So a different choice of curve will give you a different value of the action. And we want to see which value of x is going to give us the best value. This kind of looks like a derivative problem. The difference now is, instead of adding h, where h is just a number, h is going to be a small perturbation. And so what we want to do is we want to say, if we add a small perturbation, we want that to be 0. And so here epsilon is going to be a fixed extra thing. And then by multiplying by s, we're going to rescale it and make it smaller and smaller and smaller, so that as s goes to 0, we get it's basically the same as h equals 0. So the next part is now just trying to figure out, what would this derivative look like? So what would it look like to take this? Well, we plug in x, and we replace x with x plus s times that new small tweak epsilon, and then derivatives as well. We now calculate the derivative. So the derivative of this. And so we now integrate by parts, and they use the fact that the new curve that we're adding has to be 0 at the endpoints, because we can't change our endpoints. So we know this new path epsilon has to have epsilon 0 equals epsilon 1 equals 0. And so we want this integral to be 0 for any choice of epsilon. Okay, well, the other thing is, notationally, I don't like this notation. This is not raising it to the ith power, this is the ith index. This is just the fundamental lemma. The only way this is going to work is if each one of these, for each choice of I, is equal to 0. And so these are the Euler-Lagrange equations. dl dxi is d by dt dl dxi dot. And so one of the applications of this is, to physics, if we choose for our L to be 1/2 m x dot squared plus y dot squared plus z dot squared minus v x, y, z, you might recognize this is the kinetic energy, 1/2 mv squared. This is the potential energy. So this leads to the Lagrangian formulation of physics. Out of curiosity, has anybody done physics like this? Okay. So I'm not going to say too much if you haven't done physics like this, but when you go through and you say you have a central force or a conservative force, so the force is equal to the gradient of the potential, when you do the physics calculations, you end up getting mx double dot is negative dv dx. And this is essentially F equals ma. This is the force equals mass times acceleration. So you can recapture Newton's second law if you rewrite physics as saying we are trying to minimize the action. So again, this should hopefully be amazing seeing something like this. That Newton's second law, where does it come from? It comes from trying to minimize the action. So there's a lot of things in mathematical physics where the answer is a minimizer. The surface that wire takes when you hang it between two fixed points is such that it minimizes the surface of revolution. So there's a huge, huge industry of these minimization principles. The next thing is you can actually say, well, what would happen if we had some constraints? And so I grabbed this from math stock exchange, where we have a normal extremal that we want to minimize, but now we want to add a constraint. And there's ways to do this very similar to the Lagrange multipliers that we did earlier today. So again, there is an entire subject of calculus of variations. It was a wonderful semester-long class. We're not going to cover all the material in a semester, but the hope is to give you a sense of the types of problems that calculus of variations can do. So the simplest is when we have an object that we just want to minimize. That's some kind of integral involving a curve, the derivative of the curve, and the time. But you can add constraints as well if you want to have constraints. All right. And then the very last thing to do, I hope this is visible on your screen, is to just show you yet again connections between math and physics. So can somebody state what the uncertainty principle is?
In math terms?
In physics terms, but that's a great question in terms of which way do I want it.
Well, from the high level, it's just that, like, the more accurately you know the position of an object, the less accurately you can know the momentum.
And
that's what I learned in physics class, at least.
Yep, great. One way to think about this, if you want to understand where something is or where it's going, you have to have an interaction with it. And if you want to measure something precisely, you would need to use a photon with higher and higher frequency, which would give it more and more of a kick, which would change its momentum. If you have a large object like the moon, it is not a big deal to measure where the moon is accurately. The photon of light hitting the moon is not going to have a huge impact. But on the subatomic scale, when you hit an electron or a quark, completely different story. It turns out that you can recount the uncertainty principle as a statement about the function and its Fourier transform. And
Yeah,
yes?
I think we went over this, or we mentioned this briefly in one of the lectures.
Right, we mentioned
the idea that the more spread out your function is, or the more variance it has, the less variance its Fourier transform has, right? Or maybe it's the other way around. I could be.
No, it's the other way around. If the more concentrated a function is, the more spread out its Fourier transform is. It might be that both of them are spread out. But the big thing is that there's a nice lower bound. And so we have basically two operators, position and momentum. And the physics is that if I have some function f, and let's say f is going to be the density of my particle. So that means that the integral of f squared is going to be 1. The position operator would just be multiplying by x. So its expected position is just multiply by x and integrate. Its variance is you look at the integral of x minus the expected value squared times the density. And the physics is that the position operator q is just x times f of x. And the momentum operator is just 1 over I times the derivative. And again, beyond the scope of this class to say why this aligns with physics, but we can forget about physics and just say, well, let's just define these two operators. And one of the reasons this is worth doing is we saw that the derivative of a function is related to things involving the Fourier transform. And so when we take the Fourier transform of the derivative, it's going to turn the derivative into a multiplication. And so when we look at that, we can get the expected value of f hat and the expected value, and then the variance of this. And the result is that the variance of the position and the momentum operators together have to be at least so big. And so in math world, it's at least 1/4. In physics, you now have the Planck constant, and that's where it's going to be h times p. And you have this fundamental inequality that you can't know the position and momentum arbitrarily well. But given that we spent a lot of time developing Fourier analysis, I thought it would be nice to just end with a wonderful application. There is a terrific article by Wigner, I will try to remember to find that and send that to you, on the unreasonable effectiveness of physics, of mathematics and physics and the sciences. Is that physics and other fields can be so well described by these mathematical systems that we've developed. What's going on here? All right. So anyways, it has been fun discussing the material. Let me just stop recording for a second.